I want you to imagine, just for a moment, that you are packing a suitcase for an incredibly long trip.
Oh, yeah. The absolute worst.
Right. It's a universal struggle. You're probably doing what every single one of us does when you're faced with a tiny bag and, way too many clothes.
You try to fold things smaller.
Exactly. You're rolling your shirts up into those tight little fabric tubes, or, if you're really hardcore, you've got those plastic vacuum seal
Oh,
bags.
right, where you literally hook up a vacuum and suck all the atmospheric air out just to flatten a sweater.
Yeah. Just trying to win that game of physical pressure. And that, essentially, is how we've handled traditional data compression for, well, the last 50 years.
It really is. It's the exact same concept.
If you're holding your smartphone right now, or if you're screaming this deep dive on a laptop, your device is constantly doing that exact thing.
Just squeezing data as hard as it can.
Right. It's taking your photos, your text, your audio, and just crushing it down to make it fit into your limited network bandwidth or your hard drive.
But, and this is where the physics get really strange, what if there was another way?
Yes. What if, instead of squeezing your clothes, you could fundamentally alter the geometry of the clothes themselves?
Which sounds completely impossible.
It does. But imagine holding this massive, bulky winter jacket, and instead of rolling it up, you run it through a mathematical process.
A process that analyzes the actual topology of the jacket.
Exactly. The way the threads cross, the loops, the empty spaces in the fabric. And it turns that entire complex object into a single, mathematically defined, microscopic dot.
Taking up literal zero space.
Right. You just drop that dot in your suitcase.
Yeah.
And when you get to your hotel, you just reverse the math, and boom, the dot unfolds back into your winter jacket. Untouched. Welcome to the deep dive.
I mean, it sounds entirely like science fiction, but what we're looking at today is exactly that paradigm shift.
And the reason we're talking about this today is this breathtakingly ambitious software project. It's called Bitwise.
Right, and if you just read the surface level documentation, the developers bill it very modestly.
Yeah, they call it RIP-GREP, but for genomes.
Which, for the non-developers listening, RIP-GREP is just a wildly popular, really fast search tool for text and code.
So a fast search tool for DNA, which is cool. I mean, that's a cool piece of software on its own.
But it's a massive understatement.
A total understatement.
Yeah.
Because as we dug through these sources, the white papers, the documentation, we realized this is actually a ground-up reimagining of how we handle data.
How we compress, transmit, and secure practically everything.
We're talking about fundamentally altering the shape of human DNA, human voice, AI weights using topological math, and 54-dimensional structures.
And to really understand why this is so revolutionary, we actually need to start with the biggest bottleneck in tech right now.
Which is unequivocally trying to talk to artificial intelligence.
Right. The whole industry is obsessed with large language models.
But there is this massive friction point. If you want an AI that you can just speak to natively out loud, you have to get your voice to the server instantly.
And audio is heavy. It's so heavy.
Yeah, if you record your voice as a standard WAV file, it's massive because it's capturing the raw acoustic waveform.
It's literally plotting the physical air pressure hitting the microphone thousands of times every second.
Right, so developers naturally try to compress it. You might use FLAC, which is lossless.
But FLAC only shrinks the file by what, maybe 50%?
Exactly. It's still way too big for a real-time zero latency conversation with an AI.
So then the industry pivots to lossy compression, stuff like Opus.
And Opus is fantastic. It can
Yeah.
crush a voice stream down to about 12 kilobits per second, but it has to throw data away to do that.
It basically guesses which frequencies your human ear can't hear, and it deletes them.
And this is the realization the Bitwise team had. The LLM doesn't have human ears.
Right. The AI does not care about waveform precision. It doesn't need the exact acoustic pressure waves of your living room.
The AI only cares about the linguistic intent. It cares about what you actually said, not the physics of the air that carried the words.
And that exact realization births the first major system we see in Bitwise, which is the Numa Voice FLAC architecture.
I love that name, Numa.
Yeah, it's great. So instead of treating voice as one big, chunky audio wave, they slice human speech into 3 distinct layers.
Okay, break those down for us. What's tier 1?
Tier 1 is just the linguistic content, the phones.
So the actual mechanical sounds of the words you're forming with your mouth?
Exactly. And they compress this down to a staggering 54 bits per second.
Wait, I really want you to make sure you grasp that number. We're not talking about 54 kilobits.
No, 54 individual bits per second.
That's roughly 4,700 times smaller than raw, uncompressed audio. It is so small, it's practically telepathy at that point.
But a voice without tone is robotic. If you just send those foams, you sound like a 1980s computer.
Right, like a generic text-to-speech robot.
So they introduced Tier 2, which they call expressive prosody.
And that captures the emotion, right? The pitch and the energy contours.
Yeah. Yes. Like if you ask a question, your pitch goes up at the end. Or if you're shouting, the energy spikes.
How do they encode that without blowing up the file size?
They use signed 4-bit deltas and reset frames. And even with all that emotional nuance added in, the total stream is still only around 500 bits per second.
It's just wild. And then, just to be totally comprehensive, they have Tier 3, the lossless residual.
Because sometimes you actually do need the exact audio back.
Yeah, like if you're archiving a legal deposition or something.
Right. So for this, they use a vocoder to predict what the waveform should look like, based entirely on the words and emotion from Tiers 1 and 2.
And then, and this is so clever, they only store the mathematical difference between their prediction and the actual reality.
Which means the final lossless file ends up being 2 to 3 times smaller than a standard FLAC file.
But the real genius of this whole architecture is back in that first tier, the phonemes.
Because phonemes, when you really boil them down, are essentially just text characters representing sounds.
Okay, so this is exactly where I had to pause when I was reading the source material. I pushed back a little.
Oh, yeah. What was the thought?
I thought, wait a minute, if the phone tier is basically just a string of text characters, why go through all this exotic engineering?
Right. Why not just use standard zip files?
Exactly. Or Huffman coding, which is, the foundational algorithm behind almost every basic compression tool we use today.
It's a highly logical question, and it's actually exactly what the developers tried first.
Really? They started with Huffman.
They did. They built an entire prior iteration of this codec using a zero-order Huffman coding system, running it against a dictionary of common English phones.
So for you listening who might not be a software engineer, how does Huffman coding actually work in this specific context?
Think of it like this. Imagine you have a giant bucket of all the sounds used in the English language.
Okay, a big bucket of sounds.
Huffman coding looks at how often you reach into that bucket for a specific sound.
So frequency.
Right. So the schwa sound, that lazy sound we make constantly, is drawn all the time.
Yeah, I'm probably making it right now.
We all are. So Huffman says, great, the schwa is popular. I'm going to assign it a very short, tiny mathematical code.
Makes sense. Give the shortest names to the things you use the most.
Exactly. But if you pull out a really rare sound, like the ZH in vision, Huffman gives it a much longer code.
That seems super efficient, though.
It is efficient, but it has a massive blind spot. Huffman misses the context.
What do you mean by context?
It treats every single sound as an isolated lottery draw, but human language doesn't work like a lottery.
Right, it has rules.
Yeah. If you pull this ES sound out of the bucket, there is a massively high probability that the very next sound you pull out will be a T.
Or like a P followed by an R. Phonotactics.
Precisely, because English has structure. But Huffman doesn't know that EDS and TOL like to hang out together.
So it just writes out the full code for S and then the full code for T, totally blind to the pattern.
Which the Bitwise team realized was incredibly inefficient, so they ripped out the Huffman coding entirely.
And what did they switch to?
A system called LZ77, which is actually the underlying algorithm behind standard GZIP.
And LZ77 is different because it watches your hands, right? It uses a sliding window to look at the history of what you just said.
Yes. If it sees that CTET combination pop up again, it doesn't bother writing out the individual codes for S and T again.
It just points backward.
Exactly. It literally inserts a tiny pointer that says, hey, go look a few milliseconds back in the data stream and just copy those two sounds.
So it naturally absorbs the structural geometry of the English language. That is brilliant.
And the performance data they cite for this is wild. They ran a shoot-off.
Which is their term for a benchmark test, right?
Yeah. They ran a shoot-off using 200 kilobytes of English manuscript prose. And when they ran it through this new GZIP-backed phone codec, it hit 2.44 bits per character.
Wow. And just to put that in context for you listening, Brotli Level 11 is practically the gold standard for high-effort text compression on the web right now.
Right. It's what all the major tech companies use.
And Brotli hits about 2.35 bits per character. So Bitwise is nearly matching the absolute theoretical limit of dedicated plaintext compression.
while fundamentally acting as a lossless wire format for human voice.
It's incredible. But I'll tell you what really blew my mind about this section of the documentation.
The execution environment.
Yes, the execution environment. Because they use the W3C compression streams API, which is basically the open web standard for this kind of GZIP compression.
Meaning this entire voice architecture runs natively in standard web browsers.
Natively. It runs natively in Node.js, in Bun, in Dino, in Cloudflare workers.
The documentation explicitly highlights this. It says, 0 WASM bundles required, 0 polyfills.
And we should explain why that's a big deal. If you've ever loaded a modern web app, you know they can be incredibly bloated.
Oh yeah, you're downloading megabytes of junk.
Developers constantly have to bundle massive libraries of code WebAssembly or WizMM files or polyfills, which are basically just heavy translation scripts.
Just to get complex features to work across different browsers.
But the Bitwise voice codec relies entirely on the highly optimized C++ native libraries that are already baked into Google Chrome or Apple Safari.
You don't download any bulky libraries. You just open a browser, speak, and send this microscopic 54-bit per second voice stream.
And the server on the other side can decode it instantly. It essentially creates a universal transport layer.
Because if the phonemes round trip perfectly, meaning I can turn text into phones, send them, and turn them back into the exact same text,
Then the data packet on the network doesn't actually care if it's audio or text.
it is entirely agnostic. The exact same microscopic packet arrives at the receiver.
And the receiver just makes a choice. It says, do I run this through a vocoder to play it out loud through a speaker? Or do I run it through a phone-to-grapheme renderer to display this text on a screen?
The boundary between spoken and written language on the network completely dissolves.
It just vanishes. Okay, so that handles the AI voice bottleneck. We're compressing data down to practically nothing.
But if you're making data this tiny, the whole point is to move it fast.
Exactly. There's no reason to build a hyper-efficient pipeline if the plumbing itself is clogged. So how does the Bitwise system handle networking and memory?
This brings us to a protocol they developed called prismatic refraction.
I have to say, the naming conventions in this project are fantastic.
They really are.
Prismatic refraction sounds like a high-level magic spell from a fantasy game.
It does, but the mechanics of it are brutally pragmatic. It's their zero-copy wire protocol.
And the application contract, which is the rule for how a software program is allowed to interact with this protocol, it's defined in their documentation with one of the most vivid phrases I've ever seen in computer science.
Oh, I know exactly the phrase you mean.
The contract is literally vomit bits as fast as possible.
I genuinely laughed when I read that in the source. Vomit bits as fast as possible.
It's incredibly uncorporate, but it perfectly paints a picture of what they are trying to achieve. Unconstrained throughput.
Absolutely. Now, to understand why vomiting bits is actually hard for a computer, we have to look at how systems normally receive data.
Right. Usually when a program is downloading something, it doesn't know exactly how big the file is going to be second by second.
So the memory allocator is constantly guessing. It says, give me a 1 megabyte bucket. Oh wait, more data is coming. Pause everything. Give me a 2 megabyte bucket. Move the data over.
Those constant pauses, those microstalls, while the system literally begs the operating system for more memory, they just kill performance.
It's like trying to fill water balloons with a fire hose, but you keep having to turn the hose off to run to the store to buy more balloons.
That is an excellent analogy.
So prismatic refraction solves this using a technique called count then fill scatter.
How does that work?
Before a single byte of actual data is moved, the protocol does exactly K memory allocations.
It looks ahead.
Yes. It perfectly calculates the required geometry of the incoming data, and it sets up all the buckets in memory simultaneously.
And once the buckets are locked in,
It opens the floodgates. 0 dynamic allocations during the transfer, 0 panics, 0 unexpected crashes on external input.
okay, so how fast does the fire hose actually flow when you do that?
Running their Rust command line interface on an Apple M-series silicon chip, they hit a peak of 335 megabytes per second.
Over 300 megabytes a second, just moving data through the local pipeline.
But what happens when you take that perfectly allocated data and you have to fire it across the actual chaotic internet?
Right. This is where they introduce the client-side networking system, which is another incredible name, the Eon Fabric Canon.
The canon. And it operates on a principle they call the diversity theorem of network lanes.
Which is fascinating because if you're a software engineer building a standard app, You usually have to pick your network protocol right up front.
Yeah, you decide my app will use HTTP over TCP, which is highly reliable.
Right. It checks that every single packet arrives in order. It's what you use to download a bank statement.
Or you decide my app will use UDP, which is incredibly fast but careless.
Yeah, it just fires packets and doesn't care if they get lost in transit, like for live video games.
Right, you commit to one architecture. But what I love about the Aeon Fabric Canon is that it completely refuses to guess which one is better.
It literally races them.
Yes. It fires the identical payload over HTTP and UDP simultaneously from a synchronized starting barrier and just watches to see who wins the race to the destination server.
It's letting the real-time physics of the network decide the outcome.
And the results of this race are fascinating because they expose exactly how modern internet infrastructure actually behaves under pressure.
So let's break down the shoot-off data. Who usually wins the race?
It depends entirely on the size of the payload. For small payloads, anything under 64 kilobytes, UDP absolutely dominates,
It crosses the finish line first.
hitting 101.72 megabytes per second. And that makes sense mechanically.
Because TCP requires that complex handshake, right?
Yeah, the client says hello, the server says I acknowledge your hello, the client says I acknowledge your acknowledgement, here is the data.
And UDP just skips all of that, just throws the data over the wall and hits the handler immediately.
Exactly. So UDP is the undisputed champion of small, fast bursts.
But what happens when the file gets bigger? Say, a 1 megabyte payload.
Here is where the physics flip. If you're racing a Rust client to a Rust server, HTTP using TCP actually wins the 1 megabyte race.
It hits almost 65 megabytes per second, while UDP bogs down to about 45.
Which is wild.
Wait, hold on. Why does UDP suddenly get slower? I thought it didn't have any overhead.
It doesn't have connection overhead, but it has severe fragmentation limits.
Oh, because of the datagram size.
Right. A standard UDP datagram can only comfortably hold a few kilobytes. So to send a whole megabyte, the system has to shatter that file into roughly 18 separate datagrams.
And suddenly the operating system's kernel is overwhelmed doing the bookkeeping for 18 tiny disconnected pieces of data.
Exactly. TCP, however, does something called a bulk write. Once that initial connection handshake is out of the way, it just opens a massive pipe and pours the megabyte through in one continuous amortized stream.
Okay, so small files use UDP, big files use HTTP because of the TCP bulk write. That seems like a very clean, solved rule of computer science.
It would be, except the Bitwise team discovered it isn't always true.
Oh.
Here is where the data gets genuinely surprising. What happens if you run that exact same 1 megabyte race, but the server receiving the data isn't written in Rust?
Oh, okay.
What if the server is written in TypeScript, running on the bun runtime?
I mean, I would assume HTTP still wins. A TCP bulk write is a TCP bulk write, regardless of what language the server is speaking.
That is the logical assumption, but the result completely flicks again.
Really?
When receiving the data in TypeScript, UDP wins the median race, hitting an absolutely absurd 480 megabytes per second.
Wait, what? How does changing the programming language of the server alter the physical behavior of the network protocol?
It has to do with how the runtime environment is architected. Rust is a systems language, deeply tied to the rigid queues of the operating system kernel.
Right.
But Node and Bun, the environments that run TypeScript, they're built around just-in-time compilers and asynchronous event loops.
Oh, the event loop.
Yeah, an event loop in JavaScript is essentially a wildly efficient mail sorting room that thrives on chaos. It doesn't care what order the packages arrive in.
So when that sudden, fragmented flood of 18 UDP datagrams hits that event loop,
The JIT compiler absorbs them simultaneously, in parallel, incredibly fast.
that is fascinating. The engine of the protocol performs completely differently depending on the asphalt of the server it's landing on.
Not exactly, but as with all things in engineering, there is a catch, a heavy tail to that statistic.
What's the catch?
While UDP wins the median speed against the TypeScript server, it fails spectacularly on the extreme tail end for very large files, like 4 megabytes. The throughput just collapses to near zero.
Does the JavaScript event loop finally choke on the chaos?
No, the event loop is fine. The source material is very clear about the culprit here. It's a limitation of the macOS socket buffer limits.
The socket buffer.
Think of the socket buffer like a waiting room in the operating system. When data arrives off the network card, it sits in this waiting room until the app is ready to read it.
Okay.
By default, macOS configures its UDP waiting room to be incredibly tiny, around 9 kilobytes.
Oh, I see. So if you blast 64 megabytes of data at a 9 kilobyte waiting room.
The operating system kernel panics. The waiting room is full, so the kernel literally just locks the front door and silently drops all the remaining packets into the void.
So it deletes them.
Yep. To fix this, a user has to go deep into their OS settings and manually bump up a variable called SORCVBUF, the receive buffer, to 8 megabytes.
And most users are never, ever going to do that.
Never.
Which proves the absolute genius of the Canon's diversity theorem. You, as the developer, don't have to worry about whether your user has a misconfigured socket buffer.
Exactly. If their UDP stream hits the buffer limit and fails, it doesn't matter.
The HTTP stream, which you fired at the exact same millisecond, just quietly finishes the race, delivers the data via TCP, and the user never even experiences a failure.
It is ultimate resilience achieved through pure, unadulterated redundancy.
It's just brilliant. Now, before we move away from this underlying infrastructure, we should briefly touch on how they handle caching.
Ah, yes, because it highlights just how relentless they are about stripping away overhead.
Yeah. When the Bitwise system needs to fingerprint a cache, meaning it needs to generate a unique mathematical ID for a piece of data, so it could instantly check if it's seen that data before it refuses to use standard cryptographic hashes.
Right. And standard in this industry means SHA 256.
It's the algorithm that secures Bitcoin. It's what every major system uses to fingerprint data. Why on earth would they abandon it?
Because SHA 256 is mathematically heavy on standard laptop-class CPUs that lack dedicated custom silicon for SHA acceleration. Calculating that hash just takes too many CPU cycles.
It slows down the vomiting of bits.
Exactly. It gets in the way. Instead, the Bitwise team uses a non-cryptographic hash algorithm called XXH64.
And what's the performance difference there?
Their benchmarks indicate XXH64 is tens to hundreds of times faster than SHA 256 for the exact same volume of data. It barely registers on the CPU.
Hundreds of times faster just to generate an ID tag.
Yes. And it yields a massive secondary benefit for storage.
How so?
When SHA 256 spits out a fingerprint, it outputs a 64-character string. XXH64 outputs a 16-character hexadecimal string.
So it literally takes up less physical space on the hard drive.
Exactly. When you are storing millions or billions of cache keys in a key-value database, reducing the size of every single key from 64 characters to 16 characters, it massively reduces your storage costs and memory footprint.
It's faster to compute, and it's vastly cheaper to store. Every single layer of this project is just scraped down to the metal.
It really is.
Okay, so we've seen how they handle incredibly dense phones for AI. We've seen how they blast that data across the network, racing HTTP and UDP, and how they map it into memory.
Now we get to the really crazy stuff.
Yes. I want to transition to the original target of this entire endeavor, the reason Bitwise was built in the first place. We are moving to the genome, the Bitwise DNA engine.
This is where we return directly to your suitcase analogy from the beginning of the deep dive. This is where the concept of treating data topologically really takes center stage.
So for you listening, let's establish what DNA looks like to a computer. It is essentially a massive, billions of letters long text file made up of just 4 options, A, C, G, and T.
Just those 4 bases.
Right. And the standard linear way to compress this in Bitwise is handled by a command called BooPack. This is their 1D pack. And it is brilliantly simple math.
Because there are only 4 possible letters, you do not need a whole 8-bit byte to represent one letter. You only need 2 bits.
Exactly. Binary 00 is A, 01 is C, 10 is G, and 11 is T.
Which means you can seamlessly pack exactly 4 DNA bases into a single 8-bit byte.
Which instantly gives you a guaranteed 4x impression ratio. It never fluctuates.
And because it's such a simple, primitive bit-shifting operation, I think the docs say it uses just 2 CPU instructions per 4 values.
Wow.
It operates at a speed that breaks normal computer architecture. The system processes 465 million bases per second.
I really want to pause on that specific throughput metric.
Yeah.
465 million bases per second. The documentation points out a fascinating bottleneck here.
Yeah, the software is actually producing framed compressed data faster than a modern NVMe Gen 4 hard drive can physically absorb it.
It is outrunning the physical disk.
Yes. In traditional computer science, compression algorithms are usually compute-bound, meaning the CPU is grinding away doing complex math, sweating to shrink the file.
While the hard drive just sits there waiting idly for the data to arrive.
Exactly. But Bitwise flips the bottleneck. It is I/O-bound. The bit packing is so lean that the CPU finishes its job instantly, and the software literally has to wait for the solid-state drive to catch up.
That is the 1D pack. Neatly rolling your shirts to fit in the suitcase.
Yeah.
It works beautifully. It is efficient, but it's still linear. And this is where the developers introduced the command syzygy.
Syzygy, which is such an incredible word. In astronomy, syzygy is the alignment of three celestial bodies. The word implies connection, gravity, and structure.
And that is what this algorithm does to data. It introduces topological syzygy folding.
It completely stops looking at the DNA as a flat line of letters. Instead, it dilates the sequence.
Okay, we need to translate this for you listening. The documentation says it pushes the sequence temporarily into a multi-dimensional intersection manifold. What does that actually mean in the real world?
Think about a long physical piece of string.
Yeah.
If you drop it on the floor, it doesn't lay perfectly straight, it curves. It overlaps itself. It loops and crosses over.
Yeah, it tangles.
Syzygy looks at the linear DNA sequence and tries to find those loops in the data. It searches for repeating geometric structures.
And in biology, DNA repeats itself constantly.
All the time. For example, a geneticist might encounter a poly-A sequence, which is just the letter A repeating hundreds or thousands of times in a row.
Okay, so if the 1D pack would just tightly squeeze those A's together into bytes, what does syzygy do differently?
It treats that repeating sequence as a topological knot. It identifies the loop and mathematically collapses it.
So it's not just compressing the letters.
No, it looks at the sequence and says, this isn't 1,000 separate individual A's. This is actually just a single A trapped in a geometric loop that spins 1,000 times.
It's exactly the suitcase. It's realizing you pack two identical shirts, so you throw one out, and you just put a tiny sticky note in the suitcase that says multiply by 2.
You are compressing the geometry of the data, not the data itself.
And the results are staggering. The documentation explicitly states that a 1,000 base poly-A sequence, which would normally take up 1,000 bytes of plain text, drops down to exactly 3 bytes using syzygy.
That is a 333.3x compression ratio.
It's just magic.
And mathematically, the algorithm is treating the structure of the data as what we call an O1 invariant.
Meaning the storage cost becomes a constant.
Exactly. It doesn't matter if the sequence is 1,000 A's or 10 million A's. The mathematical knot describing it remains roughly the same tiny size.
Okay, but here is where this deep dive gets genuinely profound. This was the part of the documentation that absolutely stopped me in my tracks.
The pure entropy tests.
Yes. We know syzygy works miracles when there are loops and repeating structures defined. But what happens if you use this topological folding on data that doesn't have loops? What if you run it on perfectly chaotic, random data? Pure entropy.
The developers have a very specific term for this outcome. They call it the hope gap.
The hope gap.
And the physical result is severe, catastrophic file inflation. If you run pure entropy through the syzygy engine, the file size doesn't shrink. It expands by 8x.
It gets 8 times bigger. Why? If I am using a compression tool, why does it make my file massive?
Because the algorithm operates on what they call a faith investment.
A faith investment.
Yeah. When syzygy initializes, it assumes it is looking at biological data. It immediately dilates that multidimensional manifold we talked about. It builds a massive, complex structural scaffolding in memory, allocating huge amounts of vector capacity using a format called LEB-128 variants.
For you listening, a variant is just a variable length integer. It's a way of storing numbers that can grow really, really large if they need to.
Right. Syzygy builds this massive variant scaffolding because it fully expects to find a complex loop to collapse into that space.
It has faith that the data has a topological history.
But if the data is purely random noise, there are no loops.
Exactly. The manifold dilates, the scaffolding is erected, but it never finds a partner structure to collapse with.
There is no intersection. The mathematical space remains dilated but completely empty. You are left paying a massive file size cost for a giant scaffolding that holds nothing but chaos.
And the philosophical implication of this, the README explicitly states that hitting the hope gap is mathematical proof of non-evolution.
It is a breathtaking concept. Evolved systems, whether that is a human genome forged over millions of years of mutation and reproduction, or human language developed over millennia, they have structure.
They have repeats, they have loops, ancestry, and patterns that build on themselves.
When Bitwise tested syzygy on real scientific datasets that are highly entropic, the files hit the hope gap hard.
Like what kind of data sets?
For instance, they ran it on a BIDS particle JSON file, and it inflated by 412%. They ran it on LiDAR point clouds, which are laser scans mapping the physical dimensions of a room, and it inflated by 92%.
Because a laser scan of a bedroom doesn't have an evolutionary history.
Hmm.
It is just raw, disconnected points in physical space. It
What?
was generated in that exact millisecond by a laser. It didn't evolve.
Right.
So if your data hits the hope gap, the Bitwise kernel is fundamentally proving to you that your data has no ancestry. It has no biological or structural past. It is pure entropy.
It is a profoundly elegant way of using a data compression algorithm as an epistemological tool. You aren't just making a file smaller, you are interrogating the fundamental nature of where that data came from.
You're mathematically asking the data, were you born or were you made?
Exactly.
Okay, so we've established that the raw letters of DNA can be compressed incredibly tightly by exploiting their 3D evolutionary history. But that creates a massive new problem.
Right, the metadata problem.
Yeah. If you talk to a modern geneticist, they don't just want the raw A, C, G, and T letters. They want the context. They want the metadata. What genes are turned on? What proteins are currently binding to the DNA? What are the RNA structures?
If we've just compressed the genome into a tight 3D knot, how do we attach all that extra information without unraveling the whole thing?
This brings us to the next structural innovation in the project, the 54-dimension helix stack.
So dimension 0 is the base sequence, the raw letters.
But the Bitwise architecture allows you to stack 53 additional parallel layers of data natively into the exact same file.
We are talking about epigenetics, evolutionary conservation metrics across different species, chromatin accessibility scores, all layered together natively.
And here's where the math seems to break down completely. Let's look at the raw numbers. The human genome is roughly 3 billion base pairs long. Using their 1D packing, that compresses down to about 736 megabytes.
Which is a very manageable file size. You can fit that on a cheap thumb drive.
But if you take that 736 megabytes and you multiply it by 54 parallel universes of data, doesn't the file size instantly balloon into hundreds of gigabytes? Doesn't it become impossible to actually stream or transmit?
If you stored every single dimension linearly, like a traditional spreadsheet, yes, it would be an unmanageable behemoth of a file.
But Bitwise relies on a structural strategy they call dilation, or colloquially in the documentation, the squirrel cheek strategy. The squirrel cheek strategy. I assume that means stuffing the cheeks full of nuts, but the squirrel itself doesn't actually get that much bigger.
That's exactly what it means. It relies on recognizing a fundamental truth about biological metadata. Almost all of it is highly sparse.
Sparse meaning it doesn't happen very often.
Right. Epigenetic marks, for instance, do not happen on every single letter of your DNA. A chemical tag might only occur once every 200 base pairs.
Okay.
In a standard computer matrix, if you created a column for epigenetics, you would have 199 empty placeholder zeros, and then one piece of data, and then 199 more zeros. It wastes immense amounts of space.
Or the computer is saving space to hold nothing.
But the squirrel cheek strategy allows these sparse data channels to essentially hide in the mathematical gaps between the dense data.
How does that actually look in practice?
Let's look at the specific benchmarking data they provide for a 1 megabyte DNA sequence.
Yeah.
If you add dimensions 1 through 10, which contain all the epigenetic tagging data, it adds almost 0 bytes to the total file size.
Wow.
The file grows by a factor of 0.05x.
You're adding 10 entire dimensions of biological reality, and the file size barely twitches.
And even when you start adding the dense channels like cross-species conservation scores, which do map one-to-one with every single base of DNA, the overall expansion is rigidly controlled by the topology.
So when you activate the entire massive 54-channel stack on that 1 megabyte sequence, the file doesn't expand by 54x.
No, it only expands by 12.4x.
So you are getting 54 dimensions of deeply interrelated, complex biological data for the storage footprint of 12.
It's incredibly elegant.
And the way they architect this on the actual binary level is so clean. It all relies on a tiny 10-byte header they call a flow frame.
The flow frame is the unsung hero of this entire system. It is what makes this architecture useful far beyond the realm of biology.
Right.
To visualize a flow frame, imagine a tiny 10-byte tag at the front of a data packet. The first 2 bytes are a magic number, a specific signature, so the system knows it's looking at a bitwise frame.
Then you have a stream ID, some bit flags, the positional coordinate, and the payload length. It is entirely self-describing.
Meaning, if a totally new software program opens this file, it doesn't need to go download a separate instruction manual to know what it's looking at. The data teaches the program how to read it.
Precisely. The decoder reads the flags, which explicitly encode the bit width of the data channel, and it knows instantly how to parse the payload.
And because the frame relies on an agnostic positional coordinate system, you can plug absolutely any time series or sequential data into it. It doesn't have to be DNA.
Right. The README lists these incredible industry presets that have nothing to do with genomes. They have a preset for high-frequency trading and finance.
Oh, yeah.
It tracks 12 dimensions of market data bids, asks volume, latency at 1,000 ticks per second, natively in a flow frame.
They have a preset for autonomous vehicles tracking 16 channels of sensor data, LiDAR, radar, cameras, steering angles. An entire 8-hour driving shift right straight to a 1.3 terabyte flow frame stream.
They even map radio astronomy, 20 channels of deep space telemetry. By generalizing the flow frame, they've built a multidimensional streaming format that is bound only by the speed of an NVMe drive, applicable to almost any industrial application.
The packing algorithm simultaneously compresses and frames the data in a single pass. There is no serialization boundary. The format on the network wire is the format on the hard drive, is the format in active memory.
Okay, so we have this hyperdense 54-dimensional data structure, and we know it can fly across a network faster than a hard drive can spin.
But that introduces a massive glaring vulnerability.
Trust.
Yes.
If I am receiving a 54-dimensional knot of high-frequency trading data, or worse, someone's sensitive cancer genomics data, how do I prove who owns it? How do I verify that the data hasn't been tampered with in transit across a distributed network without destroying all the incredible speed and efficiency we just built?
This brings us to the philosophical, cryptographic heart of the project, not chain. And to understand not chain, we first have to answer a question that the developers explicitly pose in the white paper. What good is a knot?
It's a great question, because usually in daily life, if something is knotted, it's broken. A knotted shoelace, a knotted power cord. It implies chaos and frustration.
But in the Bitwise philosophy, a knot is the exact opposite. A knot is a mechanism that turns chaos into intentional structure.
Right.
When you tie a knot in a rope, you are binding a state. You are creating a permanent record of an action. Furthermore, a knot stores history. The specific over and under crossings of the thread physically encode the sequence of actions that created it.
And crucially, a knot remains measurable. You can compute its tension, its geometry, its sealing distance.
So in their view, a good knot is an auditable mathematical container for complexity.
Exactly, and they take this concept and use it to build an edge-native blockchain.
Now wait. Stop there. Blockchain?
Cryptos.
I know. When most people hear those words, they immediately think of massive environmental waste. They think of warehouses full of graphics cards burning megawatts of electricity just to process 3 financial transactions a second.
Yeah. How on earth does a heavy, slow blockchain fit into this hyper-optimized, zero-overhead Bitwise universe?
It fits perfectly because Notchain abandons the traditional architecture completely. It does not use proof of work, which is the energy-intensive competitive mining process used by Bitcoin.
Okay, so what does it use?
Instead, it uses a novel consensus mechanism called proof of knot. And this mechanism is so computationally lightweight that it runs natively on Cloudflare workers.
For you listening, Cloudflare workers are essentially tiny, ephemeral serverless functions. They live on routers at the very edge of the internet, physically close to the user. They have very little memory and very little CPU power.
Right. You cannot run a traditional blockchain on an edge worker, but
Right.
you can run Notchain. The developers note that operating an entire Notchain node costs between $0 and $7 a month. There is no mining. There are no GPUs.
Okay, so that solves the energy grid problem. But what about the speed problem? Blockchains are notoriously slow data layers. You don't store large files on a blockchain.
This is where the integration with the flow frame format shines brilliantly. They ran a benchmark to prove the throughput, and it is mind-blowing.
Tell me about the video test.
They took a 90 megabyte high-definition video file, 1440 by 1080 resolution, and they stored the entire thing directly on the Notchain, fully encrypted.
You put a whole HD video directly onto a blockchain ledger that is usually considered technologically impossible, or at least astronomically expensive?
Not with this architecture, because the blockchain is the 54-dimension columnar helix we just discussed. The blocks are flow frames.
Oh, wow.
And when they stream that video back out, decrypting the chain data on the fly from the edge network, it's streamed at 101.6 megabytes per second. That is 191 times faster than real-time playback.
191 times faster than real-time, streaming directly from a blockchain ledger. That genuinely breaks my understanding of how distributed networks are supposed to behave.
It achieves that speed because the storage overhead is practically non-existent. Traditional blockchains wrap data in massive layers of cryptographic metadata. The knot chain only adds 1.3% storage overhead to the raw data. It is nearly invisible to the pipeline.
And they're already using this in the real world for critical data, right? The source mentions a specific data set of 20 cancer genes.
Yes. We're talking about crucial life or death genes like TP53, BRCA1, KRAS. They stored this entire data set natively on-chain as 2-bit packed DNA within these 54-dimension blocks.
Every single gene gets an 864-character topology hash. The content address, the ID used to find the data on the network, literally maps to the topological state of the DNA itself.
It creates a perfect, immutable, mathematically auditable record of human genetic data, accessible instantly from the edge of the network.
But you mentioned encryption a moment ago when we talked about streaming the video. The way Bitwise handles encryption is perhaps the most audacious claim in the entire documentation.
Oh, absolutely. We have to talk about the Lacey cipher. When I read this section, I had to read it 3 times because it sounded like a prank. Let's break down the Lacey cipher.
The defining characteristic of the Lacey cipher is that it provides absolute zero overhead steganography.
Let's define steganography for you listening. It's the practice of hiding a secret message inside something totally ordinary, right?
Like writing a secret note in invisible ink on the back of a grocery list, or hiding a text file inside the pixels of a JPEG image.
Precisely. And in traditional computing, encryption adds weight. If you take a 1 megabyte file and encrypt it with standard AES encryption, the resulting file gets a little bit bigger. The algorithm adds initialization vectors, padding bytes, and authentication tags.
But the Lacey cipher adds exactly 0 bytes of overhead. The encrypted file size is mathematically identical to the plaintext file size.
So how is it actually hiding the data if it's not adding any lock and key metadata?
It rewrites the existing geometry. It takes those 54 dimensions we talked about and scrambles them from the inside. Think of it like taking a completed Rubik's Cube and twisting it 20 times.
The cube hasn't gotten any bigger or heavier. It hasn't gained any new plastic.
But the original pattern is completely gone. The Lacey cipher rewrites the stream IDs, it rewrites the positional coordinates, and it XORs the actual payload data, all perfectly in place.
So if I don't have the decryption key and I intercept this data stream on the network, what do I actually see? Do I just see a block of obvious static noise? Because normally, if a network administrator sees pure static, they know it's an encrypted file.
And that is the genius of steganography. You don't see static. Because the cipher operates strictly within the parameters of the flow frame format, to an observer without the key, the ciphertext looks like perfectly valid, beautifully structured, highly parsable multi-channel data.
The frame headers are perfectly correct. The payloads look biologically plausible. The Rubik's Cube still looks like a valid Rubik's Cube. It just has entirely the wrong values running on the wrong channels.
You wouldn't even know it was encrypted unless you knew what the data was supposed to look like in the first place.
It is invisible by construction, but the natural question any security researcher would ask is, how secure is it really? If it's not using standard, battle-tested AES encryption, how do we know this weird internal scramble can't be cracked?
This brings us to the actual mechanism, the rotating half-Lacey cipher, and the impossibility proofs that back it up. The cipher doesn't just use one static scramble. It uses 2 distinct permutations, which they call alpha and beta. And these permutations advance by 1 dimension for every single helical turn of the data.
Meaning the lock changes its shape as you move through the file?
Exactly. It is position dependent. And the Bitwise team didn't just casually claim this was secure. They proved it mathematically using a formal verification system called Lean4.
We need to talk about Lean4 because this comes up constantly in the source text. Lean4 is not just a unit testing suite, right?
Not at all. A unit test just runs a few examples through your code and says, yep, it worked this time. Lean4 is a mechanical theorem prover. It is a programming language where you write strict mathematical proofs and the compiler mechanically checks the logic down, the foundational, undeniable axioms of mathematics.
If your logic is flawed, the program simply will not compile. The Bitwise team wrote 402 mechanized theorems for this project with 0 external dependencies and 0 sorries.
For context, in the Lean language, if a math proof gets too hard, a developer can type the word sorry to skip it and force the compiler to accept it. Bitwise refused to use any sorries. They proved the hard parts.
And what Lean4 proved about the Lacey cipher is staggering. It proved that the combined key space, the number of possible combinations you would have to guess to break the encryption, is 2 to the power of 247.
2 to the 347th power. Okay, numbers that big completely lose all meaning to the human brain. Put that in physical context for us.
The documentation provides a thermodynamic proof to give exactly that context. Let's do a thought experiment. Imagine you wanted to build a supercomputer specifically to brute force and crack the Lacey cipher.
Okay.
To do this, let's assume you could somehow harvest the entire mass energy of the observable universe. Every single star, every black hole, every galaxy, all matter and radiation, roughly at tens and 70 joules of energy.
Okay, I have magically turned the entire universe into a battery.
Now, you take that universe battery and you power a computer that operates at Landauer's limit, which is the absolute theoretical maximum efficiency allowed by the laws of physics. It is physically impossible to compute more efficiently than this.
So I have a perfectly efficient universe computer.
That computer could perform approximately 10^90 operations before it consumed the entire universe and burned out. The Lacey cipher key space requires so many operations to break that it exceeds that universe capacity by a gap of over 10^600 universes.
A gap of 10 to the 600th power universes. So it's not just a matter of computers aren't fast enough yet. It is thermodynamically, physically impossible to break this cipher within the constraints of our reality.
The mechanized lean 4 theorem literally outputs the statement, gap greater than 150 orders of magnitude beyond physics.
But wait, with encryption, they have to run into legal issues, right?
Yeah.
Governments and intelligence agencies generally do not like cryptography that they physically cannot break.
You're entirely right, and the README addresses this. They note that this level of encryption forces them to adhere strictly to U.S. EAR 734.7 export compliance. They actively have to enforce strict geo-blocking on their ingestion workers because the software tool is legally classified as a munition under certain U.S. export definitions.
They were deploying military-grade, universe-proof cryptography just to secure biological data streams.
It is just staggering. But okay, let's try to bring this back down to Earth, or at least back to silicon. We have this universe-proof math, this 54-dimensional folding, this zero-copy networking pipeline. What can this technology do for the tools we use today?
Which brings us to the final section of the deep dive, sovereign mesh inference.
If you can compress data incredibly tightly and stream it securely at 191x real-time speed, you can fundamentally change how we run artificial intelligence models. Right now, if you want to run a large language model locally on your own hardware, it is a heavy, painful process.
You use a tool like a llama? You download gigabytes of model weights to your hard drive, you load them from the disk into your RAM, and you wait.
It takes forever. Sometimes you type a prompt and you wait tens of seconds just to get the first word out while the computer grinds.
The Bitwise developers ran a head-to-head shoot-off to prove their architecture. They pitted their system, which they call the Gnosis Distributed Inference Mesh, running a special .NOT formatted weights file against a standard Llama installation running the exact same Llama 3.2.1b model on an Apple M-series chip.
And what were the results of the race?
Gnosis achieved a time to first token, the time it takes for the AI to start speaking, in 3,141 milliseconds, roughly 3.1 seconds. A llama took 17,362 milliseconds, over 17 seconds. The Bitwise mesh was 5.5 times faster to start thinking.
Okay, hold on. The Gnosis mesh is pulling the model weights from a remote server over the network, right?
Yes, it is streaming them.
How on earth does streaming a multi-gigabyte file over the internet beat a file that is sitting locally on a solid-state hard drive? That shouldn't be physically possible.
It comes down to brilliant architecture and a memory trick called map. Usually when a program wants to read a file, it plays a game of telephone. The hard drive reads the file, hands it to the operating system kernel, the kernel copies it into user memory, and then your program finally gets to look at it. It is exhausting and slow.
The Gnosis mesh bypasses this entirely. When it requests the AI model, it streams it via HTTP 206 range request, pulling exactly the specific mathematical layers it needs directly into a temporary KIM file. And then it does something counterintuitive. It immediately unlinks that file.
Unlinks it, as in it deletes the file it just downloaded.
From the file system directory, yes. But because the AI process still holds an open file descriptor, the operating system keeps the memory alive in the background. The system then uses memory mapping to map those network-streamed bytes directly into the RAM space of the processor for demand-paged execution.
I want to make sure you listening can visualize this because it's incredible. Basically, instead of downloading a massive encyclopedia, saving it to your bookshelves, taking it off the shelf, and opening it to page 1 Gnosis, has the encyclopedia beamed directly onto the optic nerve of the CPU, page by page, only exactly when it's needed, and leaves zero trace on your hard drive when it's done.
Exactly. InMap is like reading the book through a telescope instead of walking over to pick it up. It completely eliminates the disk I/O bottleneck that slows down traditional local AI setups.
But building a system that close to the metal, where you're tricking the operating system with unlinked files and memory maps, has to be incredibly dangerous. It's so easy to make a mistake.
It is incredibly error-prone, and the developers actually share a fascinating anecdote about a bug they had to fix in this exact inference system. It was a hang in the verify batch function. The AI's matrix multiplication was just spinning indefinitely, reading garbage data and locking up the machine.
What caused the lockup?
A very simple dimensional mismatch in the math. AI models use something called attention heads to understand context. The developers were using the wrong dimension size for the key value projections in that attention mechanism. They used a dimension of 2048, which was the overall hidden dimension size, instead of 256, which is the correct number of heads multiplied by the head dimension.
So they told the computer to read a row of math that was 8 times too long.
Precisely. It caused the matrix multiplication to blindly read 8x past the actual bounds of the tensor, spilling over into unallocated, raw mapped memory. It's a classic low-level memory error, but it highlights exactly how tightly coupled this entire system is to the raw math. If one dimension is wrong, the entire topology collapses.
And it brings us full circle right back to the foundation of truth in this project. Lean 4. Every single one of these operations, from proving that 4 DNA bases pack into 1 byte, to proving the thermodynamic impossibility of cracking the cipher, to ensuring that matrix math of the AI inference engine is structurally sound, it is all backed by those 402 mechanized Lean 4 theorems.
They aren't guessing. They aren't just writing code and hoping it runs. They are mathematically proving the structural reality of their architecture before a single byte ever hits the wire.
So what does this all mean for us? Let's synthesize this journey. We started this deep dive looking at a desire to compress human voice so a large language model could process it faster. And we ended up looking at a 54-dimensional software architecture that proves the thermodynamic limits of the universe and can mathematically detect the evolutionary history or the pure chaotic entropy of a human genome.
The through line here is profound. This isn't just clever coding or a neat compression trick to save space on a hard drive. It is a fundamental shift in how humanity interacts with information. We are moving away from treating data as a flat line of text on a screen. We are moving toward treating data as a physical geometric object, an object with volume, with shape, with topology, and with history.
It's realizing that the structure of the data is the data.
Exactly. When you finally acknowledge the geometry of information, you unlock efficiencies that look like magic to a linear system.
Yeah.
You can hide 40 dimensions of epigenetic metadata in the sparse, invisible gaps of a genome. You can fold a 1,000 base sequence into 3 bytes. You can encrypt an entire reality with 0 overhead just by rotating the perspective of its dimensions.
Which leaves me with a final provocative thought for you listening. If human DNA, the very biological blueprint of life, if spoken language, the way we emotionally connect with each other, and if artificial intelligence weights, the simulated brains we are currently building, if all of these wildly different things can be perfectly optimized and secured by treating them as multidimensional topological knots, is it possible that all information in the universe inherently wants to be folded?
That is the ultimate question this project forces us to ask.
Think about it. When we struggle with information overload in our daily lives, when you are drowning in emails, notifications, and endless scrolling feeds on your phone, are we actually suffering from too much information? Or are we just suffering from the friction of trying to force a 54-dimensional, deeply interconnected reality into flat, one-dimensional spreadsheets and timelines? Maybe we don't need less data. Maybe we just need to learn how to change its geometry. Maybe we just need to learn how to fold the clothes instead of constantly sitting on the suitcase.